Okay. We're going to be talking today some more about linear regression. A few announcements. Homework 10 is due this week on Thursday. Thursday is Veterans Day. So there's no labs on Thursday. If you have a Thursday lab, if you're normally going to a Thursday lab, your GSI will have posted an alternate time. You can either go to the alternate time, or you could do the lab on your own and complete the entire lab with 100% of the test passing and submit by Friday at noon. Homework. Yeah. Homework is due Friday. Sorry. Shows you I shouldn't be writing these announcements first thing in the morning on a Monday morning. Okay, so if your lab was on Thursday, check Ed for the alternate time or do lab on your own, either one, whichever you prefer. What we're doing, we're in the middle right now of a module on linear regression. So today I'm going to show you about how to find the best line, the best fit line for a data set, and why the techniques we've been developing do that. And I'm going to be looking at the kinds of errors that you make if you use this regression line for prediction. On Wednesday, we will go a little deeper into the uncertainty into what that line should be, given the data we have. And then on Friday, we're going to switch topics and we're going to look at privacy in data science. The Friday lab deadline. Yeah, the Friday lab deadline is for everyone. There are no office hours on Thursday either. Thursday's a holiday. Okay, so before I dive into linear regression, I wanted to show you something cool. There's this data set we were using on Friday of data from the congressional district. This is data from the 2016 election with one row per congressional district. And it shows some stuff in there. 2016 was an interesting election where the pollsters made the wrong prediction about who would win the presidency. So there was a lot of interest in looking at the data. And here you can see some information about demographic information about each congressional district and the percent who voted for the Democrat. And I realized this morning there's something fascinating happening in this data set that really has nothing to do with what I'm teaching you today, but was too cool to not show you. So I hope I can beg your indulgence for just a moment to show you this nifty thing about this data set. Let's start by looking at how people voted in this election for the Democrat or the Republican. And for those of you who know US politics, all else being equal, who do you think is more likely to vote for a Republican, rich or the poor? Okay. And who do you think is more likely to vote for the Democrat, the rich or the poor? All right. So that's the conventional wisdom, is that all else being equal, the rich are more likely to vote Republican and the poor are more likely to vote Democrat. So let's look at what we can see in this data set to see if that seems to be what happened in 2016. So you'll notice that this data set has a median income and it has a percentage voting for the Democrat. So let's make a scatter plot. And I also put a regression line through it of income on the x-axis and percent voting for the Democrat on the y-axis. Now, what direction does this line go? It goes to the right and up, right? So is that a positive association or a negative association? Positive. Okay, so what that means is the higher the median income, the higher the percent who are voting for Clinton. Does that sound like what we were expecting? Okay, so have we disproved the conventional wisdom? Well, maybe hold on a bit before we draw any conclusions. Something's looking a little dodgy here. this is one of the most interesting moments in science, is not eureka, but that's funny. There are a whole bunch of reasons to be suspicious. One reason to be suspicious is that this doesn't look like an ellipse. So fitting a line to this is a little dodgy. Someone points out ecological correlation. You're right. This is an ecological correlation. Each data point these numbers are aggregates over an entire congressional district. It's not a single person. This is like averages over a congressional district. But there's something more happening that I want to show you, and maybe it will help us make sense of this. This data set also has, in addition to the median income in the district, it also has the percent who went to college. And remember this scatter plot? This is the same scatter plot we were looking at last time, where now I'm looking at the relationship between the percent who went to college and the median income in that district. Now, what you see here is that the more who went to college, the higher the median income. If you know anything about US politics, are college graduates more likely to vote Democratic or Republican? Yeah, and folks who didn't go to college, are they more likely to vote Democratic or Republican? Yeah. So college graduates, all else being equal, a little more likely to vote Democratic, and those who didn't go to college, a little more likely to vote Republican. Does anyone want to take a stab now at giving me an alternate explanation for this trend we saw up here between median income and the percent voting for the Democrat? Take into account what you now know about college graduation rates. College grads make more money, and college grads are more likely to vote Democratic. So the districts that have more college grads, we could expect, where would you expect them to be in this scatter plot? Which portion of the graph? The upper right. If the districts with more college graduates, you expect to be in the upper right. And if the conventional wisdom is true. And the districts with fewer college graduates, where would you expect them to be on this graph? The lower left. So in fact, this positive association we're seeing here could be accounted for. An alternate explanation is not that the conventional wisdom is wrong, but the conventional wisdom is right. That districts with more college graduates have a higher income and also have a higher percentage voting for the Democrat. And that pulls in the opposite direction as the conventional wisdom about rich people being more likely to vote for Republican. And maybe the college graduate is a more important factor than the income's direct effect on voting, hence why we see this positive association here. Did that make any sense? So how would you describe this using the language that we built up in this class? What happened here? What's going on? Is there any concepts you've seen in this class that are relevant? The R value tells you how strong the association is. Yeah, there's kind of this confounding effect, right? Where college graduation or attending college is a confounding factor. All right. And in addition, this is an ecological correlation. So just because you found a correlation doesn't necessarily mean that there is causation. In fact, actually, things could be the opposite way that it looks. Confounding factors could have such a powerful effect that the true effect could go the opposite way than it looks if you were to just look at the association in the data. Isn't that awesome? All right. Thank you for living with me for a moment there and enjoying this this amazing aspect of this data set. So back to our regularly scheduled topic. I want to talk to you about regression lines. So we were working last time with this data set where we were trying to predict the median income of a district based on the college percentage and seeing how well could we predict it. And we started to look at what the error would be if we used this regression line to make a prediction. So you can use this yellow regression line to make a prediction. If I told you that 50% of a district went to college, then you could go look up that point on the yellow line, and that would make you predict, oh, probably about $85,000 will be the median income in that district. And your prediction might be too low, maybe the true number is higher, or it might be too high, maybe the true number is lower, but that'd be your best prediction. So we can compute the error in our prediction, and then try to analyze the quality of a regression line by looking at how large these errors are. And just looking at these visually, many of these errors are like, I don't know, 5,000, 10,000, 15,000. And we suggested a way to measure how large the errors were, which is to square all the errors so they become positive, and then take the mean, and then take the square root of that. This is kind of like a notion of spread in some sense. It's similar to the standard deviation. We got a number 9,400, which interpretation of that, a plausible interpretation, is a typical error for the prediction you get from this model might be plus or minus 9,400, or more than that, maybe 2 times that or half of that, but something in that vicinity. Okay, so what I wanted to do now is I wanted to take a look at the errors, to visualize the errors. If you look at this plot here, what I've done is I've drawn in blue the regression line. Each dot represents one row in the table. And then for 4 of the dots, I showed you the error. Okay, so let's look at this, the red line all the way on the right. We have a dot here with a college percentage at about 60%. So the prediction you would make if you using this regression line for the median income would be a little under 100,000. But you can see that the actual number was more like 105,000. So there's an error in our prediction. Our prediction was too low by about $7,000. And that error can be measured by the height of this red line. We can visualize the error as that vertical red line, because that's the gap between what we would have predicted based on the college percentage of 60% and what was actually the case for this particular district. Yeah, this is an under prediction. So this red line indicates the error. We could go to the left a little bit. Here's another district where our prediction was too high. And we can draw the red line. And the length of the red line tells you how large an error is. So you draw a vertical line from the point on the scatter plot to the line. And that length of that line is how much of an error you would have made using that regression line. So you can see some plots are far away from the line. They have a large error. And some are close. They have a small error. And a reasonable way to assess how good a fit line is to look how large these errors are. So let's try a different fit line instead of the one we got with the methods we've been looking at so far. I'm just going to put in some numbers here for a different slope and a different intercept. Not what we got with the formulas above, but just some different numbers that I'm throwing out there. What's different about this line? This line looks like it's been raised up a little bit. And you can see some of the errors got smaller, but some of them got bigger. The error for this was really quite large. Or I could try changing slope. Okay, there's another line. That visually looks like a horrible line. It doesn't look like it goes through these points at all. And that can be measured by the size of the errors being much larger. If you were to use this blue line for prediction, your predictions would often have a very large error. Okay, so a possible notion of what is a good line for use for prediction is one that leads to small errors. And this last line looks really terrible. The red bars are really big, meaning there'll be big errors in our predictions. And the first line looks decent in that the red bars are often shorter, meaning small errors in our predictions. So let's just walk through concepts now, and then we're going to look at how to work with this. So the error when we make a prediction is the difference. It's the actual value, the true value, minus our estimate or our prediction. The error can be positive or negative. If it's positive, it means that you had an under prediction. You predicted too low. We saw a way to measure the rough size of the errors sort of on average across all the data points, which is that we square all the errors to make them all positive. So we won't have positive and negative errors canceling each other out. They're both equally bad. Take the mean of the squared errors, and then we take the square root to put everything back to the right size. This is called the root mean squared error. So that was the computation we were just doing. We were computing the root mean squared error for our prediction line. And in that example we looked at, it was 9,400. You can measure the quality of a line by its root mean squared error. What's better? Do you want a low root mean squared error or a high root mean squared error? Yeah, low is better. Low means the errors are typically small. We want low error in our predictions. So we want a small root mean squared error. And intuitively, the smaller the root mean squared error, the better the line is for prediction. So a reasonable criteria for fitting a line through some data is to ask for the line that gives the lowest root mean squared error to minimize the root mean squared error. And that line is called the least squares line. Okay, so that what you imagine doing is just sort of considering all possible lines, you know, flat, sloped both ways, up, down, over, and look at the root mean squared error of all of those and pick the one that has the lowest root mean squared error. If you prefer, you could pick the one that has the lowest mean squared error. That's going to give you the same line. Okay, so this line is sometimes called the best fit line or the least squares line or the regression line. I want to now work with this concept of how to fit a line through the data. See, we've now got two concepts. One concept is the line that you compute using the correlation and those formulas. And this concept now is we could try to choose the line that minimizes the root mean squared error. So that's another possible way to select a line. So if we just visualize what we've been talking about here, the residual is another name for the error. The residual or the error is the actual value minus the predicted value. And I'm going to add to this data set the fitted value or the predicted value that we get with the line from the formulas we were looking at before, and then the error or the residual. And then we can look at plot the actual value, the predicted value, and the residual. And you can see some residuals are positive and some residuals are negative, according to whether our estimate was too high or too low. All right. Maybe it's better to have them on a separate plot. Let me switch over to my other notebook. All right, so we're talking about root mean squared error. We can compute the root mean squared error for any line using the line we got with this formulas or any other line. To get the root mean squared error, you compute the error for each data point. You get the actual value minus the prediction. That's the error. Then you square that. You take the mean of all those, and then you take a square root. And we're going to print that. And we're going to try showing what the root mean squared error is for a bunch of different lines. Okay. So here's a crummy line. and it has a root mean squared error of 30,000. That's very large. That's bad. Here's another line. This looks like a better line. It looks visually more aligned with the data points. And you can see that that does seem to be borne out in that it has a lower root mean squared error, 11,000 instead of 30,000. We said lower is better. Maybe let's do another one. It looks like this line was maybe a little too high. So maybe if I lower the line a little bit, well, now my root mean squared error went from 11,500 to about 11,000. And that looks a little closer, but maybe my line could be even lower. So maybe I should lower the intercept a little more. And now my root mean squared error went from 11,000 to about 10,600. Okay, so you could imagine fiddling with these parameters, the slope and the parameter and the intercept, to try to get the root mean squared error as low as possible. Now, let's compare to the root mean squared error that you get if you use the formulas to suggest a slope and intercept. Here we get a line that looks like it goes more or less to the center of the points visually. And what is the root mean squared error? It's even lower still than anything I got before, 9,400 instead of 10,600. Okay, so now I'm going to tell you something amazing and magical. And you might not believe it yet, and that's fine, which is that the line that minimizes this root mean squared error happens to be exactly the same as the line we got with the formulas. So these two ways of getting a line are don't actually give you two different lines. They give you the same line. In some sense, they're the same way, just explained differently. This is so cool. This is so cool because it means that the formulas we've been showing you, which visually look like they're reasonable, also have an interpretation in terms of how good a line you have for prediction. It means that the formulas give us the best possible line for prediction. Out of all lines you could imagine using, the one the formulas gives you is the one that has the lowest error for prediction. Okay, so maybe you don't believe that yet. So let me take you into a little bit of a tangent, and then I'll try to show you to give you a little more confidence in that claim I just made. That wasn't a proof, that was just an assertion. I want to teach you for a moment a little bit about numerical optimization. In machine learning, numerical optimization is often used, in other areas of computing too. And what numerical optimization is, it's a way of, if you have a formula, if you have some kind of a curve or something like that that gives you a formula, find the value of x that is the lowest point on this curve. Okay? Or in other words, the value of x, if you plug that into the formula, gives you the smallest possible number from the formula. So if you have any curve or any formula, you can use numerical optimization to try to find that point. And there are techniques that computer scientists and statisticians have built up for doing optimization. And the details of how it works is beyond the scope of this class. You can take an upper division class to learn about how they work. It's really cool theory behind it. But for purposes of this class, we're just going to take it as something that someone else has built and figured out how to do, and we're going to just use it. Now, why is that relevant here? Here we have a formula we care about. We care about the root mean squared error, or the mean squared error. That's a formula that depends on the slope and the intercept of the line. So what we're going to do is we're going to use numerical optimization. We're going to use this minimization to find the values for these parameters that, when you plug into the formula, gives you the smallest possible mean squared error. Okay. So in Python, well, in the data science library we give you, there is a function called minimize that will do this process for you. You Call it with one argument. The argument is the formula that you want to be minimized. That formula you have to code up as a function. Okay? And minimize will find the arguments to that function that make that function produce the smallest possible output. So in this case, what we want to do is we want to find the line that has the smallest possible mean squared error. So we're going to code up a function that computes the mean squared error of any line. And then we're going to use minimize on that to find for us what is the slope and the intercept of a line that makes this function give the smallest number. In other words, that has the smallest mean squared error. And then that will be the best fit line, or the line that is best for prediction. So let's do it. Let's look at numerical optimization, and then let's apply it to finding the best fit line. So I'm going to start with a much simpler example. I'm going to start with a formula that has outputs a number based on the input x as a simple quadratic. All right, the formula is right here. And I've plotted it for you so you can get an idea of what this formula is doing. Now, if you were to look at this formula, what value of x would you say is the lowest point on this curve? Or in other words, makes y the smallest? 2, right here, 2. You can just read it off this graph. So we, looking at this graph, can immediately see the answer should be 2. Python doesn't know how to read graphs, but it does have a way to do numerical optimization. So let's show how to use numerical optimization to find the lowest point on this curve here. What we need to do is we need to define a function that represents the formula we care about. So we're going to make a function here called f. It has one input, the x value, and the height depends on x. It's given by this formula. So we have this return, f returns the value of this formula for a particular choice of x. And then we call minimize with this function. And minimize does some magic stuff. It's amazing, to find an x that will make f of x be as small as possible. And what it gave us here was 1.9999999. So not quite right. We know the correct answer was 2. It was just a teeny bit off, but it was so close. Okay, so how does minimize work? You can think of it as trying lots of values of x and then keeping the one that worked best, except you would have to try a lot of values of x. So it has a smarter way to like try different values of x and figure out whether you should choose one that's bigger or smaller, and it gradually converges in on something that's very close to the correct value. Yeah, if you know something about this topic, gradient descent is a method you could use for optimization. And if you know calculus with this particular formula, you could use calculus, but you don't need to know either of that for this class. Now, the cool thing about this technology, it's like this black box that is indistinguishable from magic, is that it works not just with simple formulas like this, but it works with more complicated formulas. So for instance, here is a more complicated formula with like some sine stuff happening and some x cubed and crazy stuff. And there's our formula. And then we can ask this to minimize the formula. And now, wait a minute. What am I doing wrong here? What? Well, that was crummy. I'm plotting the wrong function. Let's try again. That's what this formula looks like if I plot it. So some crazy curvy thing. And if we use minimize, visually we can see it should be about negative 0.5, but maybe not exactly. Minimize tells us actually, no, sorry, it was negative 0.51. Okay, and you could do a more complicated function. This minimize thing is happy to take as complicated a function as you got. So let's now apply this amazing technology to find the best fit line. So what we need to do is we need to define a function that represents the formula. Now, what we're going to try to minimize is the root mean squared error. That depends on the slope of the line and depends on the intercept of the line. So those are going to be parameters to this function. And then there's a crazy complicated formula for computing the root mean squared error of that line. It depends on all the points in the data set. And we got to make a prediction with that line and compute the error and then square those errors and add up all those squared things and take the square root and like, oh my gosh, so much stuff happening here. But no worries. Numerical optimization is fine to work with a complicated function like this. So here's our function. If I give it a particular line, like one of the lines we were playing around with before, this computes for me the root mean squared error. And here was another line we were playing around with before, the crummy line that had a root mean squared error of 30,000. And I was playing around with fitting in different numbers here to this function to try to make the output be as small as possible. And that would correspond to a better and better line. But instead of playing around with it to just by trial and error, I can use numerical optimization. And the numerical optimization will tell me that the best choice of line and intercept that minimizes the root mean squared error is 1270 as your slope and 20,800 as your intercept. And now let's compare that to the number, what we got from the formulas. And you may notice that the formulas gave us 1270 and 20,800. Almost exactly identical line. And this is not a coincidence. You can try this on any data set you want and compute the line you get with the formulas, or you can compute the line that you get by minimizing the root mean squared error, and you'll get the same line. So what this tells you is that the linear regression line is the best one for prediction out of all lines, out of all linear ways of predicting. It's the one that minimizes the root mean squared error. Yeah, minimize is so cool. It can handle functions with multiple arguments, no problem. I wouldn't want to try to plot this. I would now need a 3D plot to try to plot this. And what if there were 3 arguments? Then I would need a 4D plot. Oh, I don't even want to think about that, but no problem for Python. So let's take a little bit of a digression here. But before I do, I want to check if there's any questions. Take a pause. Can we go backwards? Can you compute the slope and intercept using minimization? In fact, that's exactly what I did here. That's what I was doing. I was using minimization to find the slope and the intercept that had the lowest root mean squared error. Can I re-explain the demographics RMSE function? What this function is doing is it's putting in one function something that computes the root mean squared error of a line with slope given by any slope and intercept given by any intercept. So when I called this function with the arguments 1500 and 20,000, that was computing the RMSE error of a slope of a line with slope 1500 and intercept 20,000. In other words, the line y equals 1500 times x plus 20,000. This is computing the RMSE error for that line. And how does it do that? Well, it gets a prediction or an estimate for each data point in the data set. This is now an array of estimates, one per row in the data set. And this is the actual value. Y is the actual value. We compute the error. Remember, the error is the actual value minus the estimate, or the actual value minus the prediction. That's the error. And then we square it. So we square all those errors. We have a whole bunch of squared errors, one per row in the data set. We take the average of those squared errors, and then we take the square root of that. Is it common practice to calculate both the regression line and do minimization? Nope. Nobody ever does that. You could do it if you wanted as a cross-check, but it turns out there's a mathematical theorem that says, no need, you're always going to get the same answer. Always, 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 every time. So I can't prove to you that theorem in this class, but I wanted to show you an example to make it feel plausible, and then hopefully you'll take it on faith from me that those will always give you the same line. If you wanted to do both just as a cross check, you're welcome to, but there's no need. Okay, so let's look at how you could use numerical optimization to find a better model if you don't think that a line is the best way to make a fit. This is a little bit of a tangent, but I just wanted to show you this. Here's a data set of how far an athlete could throw a shot put, and how strong they were in terms of how much weight they could lift in a particular way. So this is reported in a scientific paper on sports science. And you can see here's the data set. And it makes sense that the people who were stronger were able to lift a heavier weight, were also able to throw the shot put further. So yeah, good reason to go lift if you want to throw the shot put really far. So we could now try to find a fit line through this to model how much, what the association is between these two variables. So let's find the best fit line using this numerical optimization procedure we have here. And numerical optimization says a slope of 0.09 and an intercept of 5.9. So we're going to make a prediction using that fit line. And the predicted line you get is yellow. And if you look at that, maybe it's okay, but it's a little dodgy. Because to me, I'm not sure this is a linear association. It looks a little curved to me, doesn't it? The actual values are low on the left-hand side and then high in the middle, and then they look like they might start being low on the right-hand side again. So I'm not sure whether a line is the right fit to this. And the researchers who did this research said, we actually don't think a line, and we don't think linear prediction is the right, should be the right thing, just based on their understanding of biology and human mechanics and so on. They said, we actually think there's reason to believe that a parabola makes more sense. So let's try to find the best, sort of the best fit line, the best fit parabola. Everything we've been looking at generalizes to finding the best parabola. There's a whole bunch of parabolas, you know, curve this way, like this, you know, there are all sorts of parabolas. For any parabola, you can compute the errors in the predictions that you would get if you use that parabola for prediction, and then compute the RMSE of that parabola. And smaller is better, means that that's a better parabola for prediction. So let's try to find the best parabola, the one with the lowest RMSE. The formula for a parabola is you need three numbers, a times x squared plus b times x plus c. Now, I don't know what is the best value of a, b, and c, but we're going to let numerical optimization figure that out for us. Okay, so here our prediction, our estimate, was based on the value of x, how much weight they could lift, and the values of a, b, and c, which we have yet to choose. And then we compute the RMSE over this entire data set of any particular value of a, b, and c. So now we use numerical optimization to ask it to give us the value of a, b, and c that minimizes the RMSE. And it gives us these values for a, b, and c. It suggests lead to the best parabola. So let's visualize that. Here is the best parabola. You can see it's curved a little bit downwards. And to me, that visually looks like it might be better, maybe. Okay, so if you ever have a situation where a line is not the best fit, where you don't have a linear association, but something more complicated, one nice thing about numerical optimization is that you can use it to find a parabola or some other kind of fit. The formulas we've shown you only work for a line, but if you need to look for other kinds of prediction, you can use numerical optimization to find it, even though you can't use the formula. And in fact, modern machine learning is more or less based on this idea right here, plus numerical optimization. All right, so that's a bit of an aside. I want to go back.
David,
yes.
Could I please say one thing about this parabolic curve? It should be in the book, and we'll put it in. We use the parabola here because the scientists in the journal said, you know, use that as a model. But, you know, you look at the top of the parabola and it looks like it's just beginning to come down. And that's a very strange model because the association is positive. So it's really important when you use a curve like a parabola to only make your predictions in the range of your data. Because if you extend, then you might start getting very weird conclusions. That's all. End of little cautionary remark.
Yeah, good point. It would be crazy to predict that someone gets even stronger. They're not going to be able to throw the shot put as far. That doesn't seem like it could be right. All right. So that's numerical optimization. I want to go back to linear prediction, because often a line is a reasonable, good starting point. So let's focus in on lines a little bit more and prediction using the best fit line. I talked about errors. Remember, the error is the actual value minus the estimate. We talked about computing the RMSE as a measure of the size of the errors. The residual is another name. It's just a fancy word that means error that gets used when we're using linear regression. Okay, so the residual is this error. It's this difference between the actual value minus the prediction. In other words, the observed value of y minus the estimate or prediction of y that you get from the regression line. Okay. So it is the vertical distance between the point in the scatter plot that represents the observed data and the line that we're trying to fit to. Okay. So we were looking at this before. I got a little ahead of myself on this, this plot here. But the residual is the distance, vertical distance between a dot and the fit line. Let's see. Where did I have what I wanted to show you? Here, see these visualizations? This vertical line, this red line, that's the residual. That represents the error for a particular point in the data set. Now, residuals can be very helpful looking at them to understand whether a linear model is a good choice. You should only use linear regression if you think there is a linear association in the data. So you could look at the scatter plot and see whether the data looks visually like a linear association. But I'm going to show you some additional diagnostics you could do to check whether using linear regression is a good idea or whether it might potentially have some dangers or some pitfalls. So let's look at a data set that scientists collected on these adorable animals called dugongs, which they're not manatees, but they're like manatees. They're this kind of aquatic vegetable eating herbivore mammal, and which are, I don't know if they're endangered, but I think they're at risk. Okay, so what we're going to do is we're going to look at the residuals. We're going to plot the residuals. So here we have a data set that scientists, biologists gathered on dugongs, where they show for each dugong that was measured the length of the dugong and the age of the dugong. So we could look at a scatter plot here of the data. Now, looking at this, do you think there's a linear association here? Little bit dodgy. I'm not super feeling it on the linear association. I mean, maybe, but I kind of see this curved phenomenon happening here, which makes me suspect that there is an association, but maybe not a linear association. So we could try to fit a regression line. We could try to fit a linear line through this data. We could compute a correlation, which is a measure of how strong a linear association there is. And the correlation coefficient R is 0.82. 0.83. That's very large. That would be very strong association for a linear association. So let's take a look at what happens if we use a linear best fit line through this data. You can see the kind of funny curve thing happening here, where it looks like on the left side, the data is above the line, and the right side, it's above the line. In the middle, it's below the line. And if we look at the residuals, what do you expect the residuals to be on the left side? Positive or negative? Positive. The actual is higher than the prediction. Actual minus prediction is the residual. What do you expect the residuals to be in the middle? Negative. And what do you expect the residuals to be on the right? Positive. Okay, so let's look at the residuals. You can see the residuals are positive on the left and positive on the right. In the middle, they're kind of lower. They're 0 or negative. So this is one indication that you might not have a linear association. When you can see a pattern in the residuals, like when you can see here, that's reason to be suspicious that you may not have a linear association. Okay, let's go look up at an earlier data set. Here we had the demographics, the congressional districts we were looking at before with some fit line. And then we look at the residuals, a plot of the residuals. And here the residuals, there's less of a pattern here. So this is better. This is a better, you don't see some kind of curve or some trend in the residual plot. That is better sign for linear regression. When you see some kind of a curve or a trend in the residuals, that's a worse sign for linear regression. So if we were using linear regression with dugongs, maybe you should be a little bit careful, be a little bit suspicious. Let's take another example here. Let's look at US women in the US. And we're going to look at their height, and we're going to look at their weight and the relationship between height and weight. Look at that. Does that look like a strong association? Oh my gosh, yes. Let's, actually, as I look at this again, I realize I should introduce this data set a little bit better. These heights here, each data point is not a single woman. This is the average weight of women with that height. Okay, so it looks like there's a really strong association here. It is ecological. You're absolutely right. So we could try to fit a line and compute the correlation coefficient. Correlation coefficient, 0.99, really, really strong measure of linear association. Now, if we plot the residuals, what do you see here in the residual plot? Oof, yuck, a really strong pattern in the residual plot. So while visually this data looks like it's all lined up in a line, it looks really close to a line. It's really hard to see from the original data set, but the residuals plot is telling you that there is a deviation from a linear association. And if we look at the fit line in the data points, maybe you can see now the fit line yellow is the straight line. Maybe you can see the blue dots are curved a little bit. There's a teeny bit of a curve to it. So this is indicating that while there is a very strong linear association, there's also a sense in which this data have some nonlinear association going on. And you should be cautious about using the linear fit line to make predictions, especially where are the errors the largest? What values of height will tend to give you the largest error if you use the best fit line for your prediction? Yeah, on the edges. For the tallest and the shortest women, you're going to have the highest errors. So you should be especially cautious about using this best fit line if you're trying to predict the average weight of very tall or very short women. There's more we could say here, but I think I'll stop here And we'll continue on Wednesday with more about using linear associations and linear regression to understand your data. Thank you.